Hi, thanks for joining me. Today I've got an interesting problem about invertible matrices. Suppose we have A and B invertible real n by n matrices, such that A plus B is also invertible, and A plus B inverse equals A inverse plus B inverse. Prove that the determinant of A equals the determinant of B. So in other words, if we have these conditions up here satisfied, then it must follow that the determinant of A equals the determinant of B. Okay, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so I'm going to start by doing perhaps the most intuitive thing, and that is just multiply both sides by a plus b. On the left, that just gives me I, and on the right hand side, I get a plus b times a inverse plus a plus b times b inverse. If I expand and simplify, a times a inverse is just I, plus b a inverse, plus a times b inverse, plus b inverse, which again is another I. So this I cancels with one of the i's here, so we get this thing here just equals 0. And now what can we do with this? Well, if I just call this matrix here x, then I have a look at this thing here and I go, this thing here is precisely x inverse. Because remember, to work out the inverse of two matrices multiplied together, you kind of swap them and then take the inverse of them. So in other words, if I have two matrices, say C and D, CD inverse is equal to D inverse C inverse. So this matrix here must be x inverse, and of course this is still I. So I have the equation x plus x inverse plus I equals 0. Okay, let's get rid of this x inverse by multiplying through by x. So I get x squared plus I equals 0. So this x times x gives, this x inverse times x gives me the I there, and this I times x gives me this. And now this reminds us of a geometric sequence with the first three terms, or geometric progression where we're adding up three terms. And one thing that's quite nice about this is if I multiply both sides by x minus I, what do I get? Well, if I multiply this by x minus I, of course the right hand side is still going to remain 0, but the left hand side is, well, I'm going to get x times x squared, which is x cubed. Then I'm going to get x times x, which is plus x squared, but that's going to cancel with the minus x squared I get from this. So in fact, all the middle terms will cancel. So if I in fact write it out in full, x cubed plus x squared plus x minus x squared plus x plus I, and this of course still equals 0. This x squared cancels with that x squared, this x cancels with that, so I get x cubed minus I is 0, so in other words, x cubed equals I. Okay, so x cubed has to be equal to I, so now what I can do is just take the determinants on both sides, so determinant of x cubed, therefore equals the determinant of the identity matrix, which of course is just 1. And now we can use a famous property of determinant, and that is the determinant of two matrices multiplied together, C times D, is equal to determinant of C times the determinant of D. So what we've got here is determinant of x cubed, which is determinant of x times x times x. So this is actually the same thing as the determinant of x, all cubed, equals 1. And now this is quite nice, because therefore the determinant of x is the cube root of 1. And now this is where we use the subtle fact that A and B are real matrices. In other words, their entries are real numbers. So that means that A, B, A inverse and B inverse are all going to be real matrices, and therefore A times B inverse is going to be a real matrix, so X is a real matrix, and therefore its determinant is also a real number. And that means when I take cube roots of both sides, I know I don't have to worry about roots of unity or anything like that, and I can simply say the determinant of X equals 1. And now what is X? X is just AB inverse, so det of AB inverse equals 1. But now again I can use this property that the determinant of A times determinant of B inverse equals 1, and therefore, again using the fact that, or using a similar fact, determinant of B inverse is the same thing as determinant of B inverse. And so then multiplying both sides by determinant of B gives me determinant of A equals determinant of B, and that proves my result. So this is a nice, interesting problem to do with matrices. Whenever you see matrices for the first time, you might think this fact here is true in general for all matrices A and B, but of course, if you've seen matrices before, you know this is definitely not true. And therefore, this is quite an interesting result. So when you do have matrices A and B which have this nice property, it turns out the determinants must be the same, provided they are real matrices. And this is interesting because this point in our argument here, where we went from this line to this line, seems, this line to this line, sorry, seems like it's, not too important and you can kind of gloss over it. But it turns out if A and B aren't necessarily real matrices, this is actually not true. So I'll give that to you as an extension exercise, and maybe let me know in the comments, can you think of matrices A and B which aren't necessarily real matrices? In other words, they have complex entries, such that A plus B inverse equals A inverse plus B inverse, but the determinant of A isn't the same as the determinant of B. So I leave that as a little challenge to you. Anyway, thank you for watching this video. If you are new to the channel, please do consider subscribing and also liking this video as well. But apart from that, thank you for watching. I will catch you in the next one. Have a great day.